I'm going to go over the FRQ portion of the mock exam. Your last project check is due tonight. Make sure you have all three of them done by then. That's FRQ and MCQ. I'm going to go over how I awarded grades into Skyward based on your performance on the mock exam. If you scored less than a 70 on either the MCQ or the FRQ, which is very few people, but there are a couple, you can retake it for a maximum of 70. The MCQ will be available by this afternoon. I'm still creating it. At first, I thought I was going to have you guys do it tomorrow in class, but then I remembered, oh yeah, you have U.S. history, USC. The FRQ you can already do. You can already get on now. Excuse me. Lockdown browser isn't required for either of those. However, they are due by tonight because there's really no point. Well, not, you can still learn from it, but tomorrow's the exam, so you need to have it done by tonight. Again, this is very few people I'm talking to. Remember, the AP exam is tomorrow afternoon. Hopefully, y'all are getting in some good, effective study time. All review materials, if you have forgotten, can be found. These are the videos. The 8 strategies video, which I really recommend you watch again. I'm going to send out a reminder about that. They're on the modules. And then the notes for every unit, the multiple choice and free response questions with solutions for every unit are on the modules for the 19th and 20th of last month. Test is tomorrow. Be sure you're in Gym 2 at 11:30. You should all be doing your EOC together. The physics, I've been told that the physics students are all doing their EOC together, and they will let you out with enough time to eat lunch before you have to go take the test. Make sure you eat lunch. Make sure you get some sleep tonight. Because the brain, whether you realize it or not, does not work as well when it's not fueled. So make sure you eat, sleep, rested, fueled, and rested. Yeah. I would recommend, most of you are on A push or dual credit or something like that. Tomorrow on the EOC, just do it in like a half hour, which you probably can, and then take a nap and get nice and rested. My students usually tell me that. That's how the U.S. history EOC goes. They are given 4 hours, and they take it in 40 minutes. Yeah. And probably did just fine, right? Okay, so yeah, all that. This is where the video that I'm recording now will be. Those at home, submit your notes. Everyone here, take notes as I'm going over the FRQs. Submit them here, and then okay. So how I graded the mock exams. So this is how, I'm just going to read. The following is an approximation of how the raw percentage scores on the 2019 AP Physics 1 exam correlated with the awarded score, i.e. the 1 through 5. The data for 2020 isn't available yet, but it's probably going to be about the same. These percentage points haven't changed much from 2016 to 2019. So that's 4 tests. And it's pretty much in this range. This should be indicative. It should tell you why, and this is some of my advice for the test tomorrow. If you get a few questions that you don't know how to deal with, for the life of you can't remember, don't let that color your whole attitude. Some students, the first 3 questions are like, oh my gosh, and then they just shut down. And then because of the shutdown, they end up not answering questions that they should have. They end up not getting the partial credit on the FRQs that they should have because they've let a few questions at the beginning color their whole attitude. Don't let that happen because, as you can see, you don't need to get much, but if you get a 70, you're literally probably going to get a 5. 70 or above, raw score, you get a 5. To get a 4, 55%, right? That's probably going to get you a 4. To pass, all you need is like a 40, okay, to get a passing grade. And then obviously 2s and 1s you don't want because then no college will give you credit for those. But yeah, you don't need to knock it out of the ballpark to get a 4 or 5. You don't. Keep that in mind. Again, don't let a couple questions that trip you up color your whole attitude for the whole test. Because chances are you'll be able to, if you fight that and you end up not losing points on questions that you shouldn't because you're still confident and you're still feeling good, then you still got a real good chance of passing. So I've given you grades based on how well your performance would have corresponded to the actual AP exam scoring. Your scores in Skyward have been awarded as follows. So when I graded the MCQs and the FRQs, I looked at your total percentages and gave you a 1, 2, 3, 4, or 5. And then in Skyward, if you got a 5, I gave you 100, obviously. If you got a 4, I gave you a 90. If you got a 3, I gave you an 80. If you got a 2, which is not passing, I still gave you a 70, which is passing. If you would have gotten a 1, then you got a 60. And again, there is a retake. The FRQ is already available. The MCQ will be done by this afternoon. If you earn less than a 60, and I think that was very minutely few people, but if you did earn less than a 60, again, thankfully this is a vast minority, it indicates that you pretty much didn't put any time into prepping for the exam, which is pretty unacceptable seeing how you're not even paying for most of the exam, the taxpayer is. This was determined by noticing the following. So I gave you less than a 60, essentially a 50. If you got a 50, this is you. For the multiple choice question portion, you scored significantly lower than what you would be expected to get by pure guessing on the questions. Because if you notice, well, not pure guess, because there's a couple questions that needed the 2 answers, but 0 to 24%, you get a 1, you get 60. So you had to get pretty significantly below 24% to get 50 in the grade book for the multiple choice question portion. For the FRQ portion, you got a 50 if you put very little effort into answering the questions, had a less than 15% raw score. This really only happened when students just didn't attempt the second FRQ, which is where most of the points came from. Okay, they just left it blank. And you had more than enough time to get both of those FRQs done, whether they were done well or not. If you didn't even try, sorry, you don't deserve to pass. See today's overview for instructions on how to make up your exam if you scored less than 70. Again, the FRQ is available already. The MCQ will be available by this afternoon. All right. Let's talk about politics. No, let's talk about the FRQs. Okay. Now, because this was a short FRQ, obviously, it doesn't cover all the physics you need to know. If you did well on the multiple choice questions portion, then that means that you are pretty comfortable with most of the material. So just hopefully apply the knowledge to the FRQs as well. But these focused on a few concepts. Not all of them didn't cover projectiles, but there was a little momentum, there's a little energy, there's a little circular motion, force analysis, stuff like that. Yes, sir.
Hey, just a quick question.
Yep.
What was the four? What was the four scoring on the MCQ again? It was 57% or
54 to 69.
Okay.
Yeah. Which is above average, obviously. And the average score is a 2 point something nationwide. Nationwide, the average score on the AP Physics 1 exam is a 2 point something. So most people are actually between the 20 to 40% range. And you all are smart. You can do better than that. I know you can. This year's challenging. This year's been challenging. I know it kind of sucks, but just focus. Don't let tough questions beat you down. Work for the partial credit. I'll give you some last minute tips at the end after we talk about the FRQs. But I do want to talk about these FRQs because there were specific things that I need to address to make sure you don't lose points on them on the test tomorrow. Figures above show 3 stages of a dive performed by an athlete. During the dive, the athlete completes several rotations in midair while traveling from the platform to the surface of the water. Figure 1 shows the athlete just after jumping off the platform. Figure 2 shows the athlete rotating in midair. Figure 3 shows the athlete about to enter the water. Figure 1 shows the athlete just after jumping off of the platform. So why did I underline that? Well, several students said that the increase in angular velocity from here to here, because we know that whenever you tuck, you spin faster, right? Just like when a spinning figure skater brings her arms and legs in, she spins faster. A lot of students, I'd say a significant percentage of students, said they exerted a torque. There was a torque on them that caused the angular acceleration that changed the angular velocity. Well, that can't be the case because the torque is generated by the jump, right? If you stand on the diving board and you just jump straight up, you don't spin. So you got to jump while you're like pushing off, and that gets your body to rotate. The torque is actually in response to the normal force that's acting on your feet and your body positioning. And as soon as your feet leave the diving board, so just after jumping off, there's no more force on you from the diving board. So there's no more torque. There is a force, it's the weight force, but that acts on your center of mass. And so a force on your center of mass cannot create a torque. So it's not going to get you to spin. So a lot of students answered this first question, which I'll read in a second, by saying that there was a torque. Okay. In a clear, coherent paragraph-length response that may also contain figures and/or equations, explain why the athlete's angular speed increased between figure 1 and figure 2 whenever they tucked in, but decreased between figure 2 and figure 3 whenever they extended again. Okay, so it's not torque. It's not torque. What changes when the person goes from this position extended to tucked in? What changes? Kinda. Starts with an I. Rotational inertia, moment of inertia. So it's the rotational inertia, okay? Now what you want to get away from, and I'm not sure if they would take points off or not, but the word radius, a person doesn't really have a radius. If a person is spinning, each little part of that person, each little piece of the mass of that person does have a radius that it's moving in a circle about. But you have to account for all of those radii, for all of those different pieces of mass. But when you account for all that, what you're really talking about is rotational inertia. Okay. And so when the person starts out, or actually when the person goes between figure 1 and 2, they take that I and they decrease it. Because the closer the mass gets distributed about the center, about the axis of rotation, the smaller the rotational inertia becomes. Because again, every little piece of mass, every little point mass in the person has rotational inertia mr squared, where r is the radius of those little pieces of mass. And so the closer they are to the axis of rotation, the smaller the rotational inertia gets. So instead of calling it the radius, it would be more better. That's how you would say it, right, in proper English. It would be more better to describe it in terms of redistributing the mass closer to the axis of rotation. Okay, but it means the same thing. You know what you're talking about, but yeah. Or you could just say rotational inertia. As the person tucks in, their rotational inertia decreases, and then that we obviously know that corresponds with an increase in angular velocity. But what relates these two? We have two equations that relate this, right? Torque talks about angular acceleration. Torque talks about the force that's causing the torque. But once you leave the diving board, there's no torque. And so that's not a valid approach to this problem. What is a valid approach? Angular momentum. Because isn't angular momentum exactly equal to the product of rotational inertia times angular velocity? And so if this is constant, and that's the thing, and that's what makes it convenient. Angular momentum is constant. Some students try to go from an energy standpoint, which is possible, but much more tricky. Angular momentum is because kinetic energy, as we'll see in the next part, isn't constant here. It's not a constant, it's not conserved. Angular momentum most definitely is conserved, always, in collisions, in changes in rotational velocity due to changing rotational inertia, just like linear momentum is always conserved, whereas mechanical or kinetic energy is not. So yeah, between 1 and 2, rotational inertia goes down, angular momentum goes up because momentum is conserved. Angular velocity goes up because angular momentum is conserved. And then between 2 and 3, they distribute the mass farther away from their axis of rotation, and therefore the angular velocity goes down. So one of the points that was awarded, the first point that was awarded, says the student recognizes that angular momentum is the way to go. Conservation of angular momentum. That angular momentum is conserved. Okay. And then going from figure 1 to figure 2, rotational inertia is increased, so angular velocity is decreased. From figure 2, reverse that. And then figure 2 to figure 3, angular rotational inertia is increased, angular velocity is decreased. Okay. All right. Part 2, or number B, says, is the rotational kinetic energy of the athlete in figure 2 greater than, less than, or equal to the rotational inertia at the beginning? So is there rotational energy here bigger than or smaller than their rotational energy here? Well, rotational kinetic energy is 1/2 I omega squared. I and omega are inversely proportional. If one goes up by a certain amount, the other goes down by the same amount, right? Which tells me what's more important as far as the kinetic energy is concerned. Angular velocity. So the rotational energy here is higher in the second. Higher rotational kinetic energy. Why is it higher? Because according to that equation, which you can invoke in your justification, the angular velocity is more important. The angular velocity gets squared, and therefore if angular velocity and rotational inertia are inversely proportional, that guy plays a much larger role in the total rotational energy than the rotational inertia of the object. And understand too that it's not like that energy just comes from nowhere. If you're spinning around real fast and your arms are like sticking out like that and you're spinning real fast, it takes work to bring your arms in. Right? You got to work to pull your arms in. And so that work that you do by the work energy theorem translates into the increased rotational energy. Right? If you're on one of those old school merry-go-rounds or that were on playgrounds, and you're standing on the edge and it's spinning around real fast, you got to work to get to the center. And as you get to the center, it's going to speed up. Because the work that you're doing to get to the center will increase the rotational kinetic energy of that system. Energy is still conserved because you're consuming the energy from your body, that you get from the food that you ate. But the kinetic energy will definitely increase. Okay. So K rot 2 is bigger than K rot 1. So angular momentum is the last thing we covered. Angular momentum. And then using that for rotational energy. Okay, number 2.
Wait, why does it say part B alternate solution on our grade?
Ignore that. I gave you credit for the solution that you addressed and then put 0 for that. And then from the 20, there's 21 points total. I took that down to 19. So I eliminated those points. That was it. The College Board shouldn't have awarded points for both the solution and the alternate solution. They put 2 points in for both, but I only gave you 2 points if you got it right, and then just deducted that extra 2 from the total score. Okay, a passenger compartment on a rotating amusement park ride contains a bench on which a book of mass MB is placed, as indicated by the dot in the left figure above. The compartment moves with a constant angular speed about the center of the ride along a circular path of radius r. The bench remains horizontal throughout the compartment's motion. The right figure above shows a magnified view of the compartment, so that's this right here. The graph below shows the horizontal component of the book's position as a function of time, where the positive x direction is to the right. Now understand where this is, what this is actually graphing. This is my x position. This is the number line that's indicating position. At 0, it's at its bottom. When the book is here, its position vector, which we call r because it's in both dimensions, is there. But what we're graphing is the x component of the position, right? That's what we're plotting here. And so from the start, we're moving in the negative direction in the x direction. Then we come to the maximum distance, which is here. Then we start going back, and then we're back at the origin, right? Yes, I know we're up higher, but we're only plotting the x component. And then we go to this end, and then we go back down to the bottom. So this is just like simple harmonic motion. Remember objects that move in a circle? If you just concentrate on either the x direction motion or the y direction motion, it behaves just like a simple harmonic oscillator. So when I plot that, right, start at the origin, I'm plotting the position in the x direction versus time, start at the origin, and then I move in the negative direction until I get to the maximum displacement all the way on the left. And then as I go around and approach the origin in the x direction from the top, I come back to that point, right? That's when it's at the top. And then he goes all the way to the right, and then he comes back to where he started. And so back to where he started is one full period of rotation. Those of you in pre-cal, I would say and calculus, but not calculus because they're doing their AP exam right now. One period, you should know, for a negative cosine graph, which this would be, is that, right? That's the time it takes the book to go around exactly one time. And that time, if I look here, well, this is 100. This is 200. There's 5 divisions in there, so each division is 20 seconds. And so it happens right here, so that's 120 seconds. That's the first question said. I don't know if I said that. First question, AI, determine the period of revolution of the book, 120 seconds. A lot of people are doing equations and stuff. They're trying to answer that question using math. You just had to look at the graph. You just had to look at the graph and know what period of revolution was and how to get that from the graph. Okay. So yeah, a lot of people overthought that one. A lot of people overthought the second one too. Calculate the tangential speed, VB. And note, this was kind of funny, guys. Literally says not says underline, not the angular speed. There's a handful of people that calculated what? The angular speed. Okay. So obviously you're not getting full credit if you calculate the angular speed. Calculate the tangential speed. And so what I saw a lot of, and this is okay if you start this way, but if you start this way, you soon realize, oh, I can't do it this way. Well, I know that the centripetal acceleration, because I know the book's moving in a circle. I know the centripetal acceleration is VB squared over R. Oh, I know the radius, so I can use this to solve for VB. That's what they're telling me to solve for. Square root of radius times centripetal acceleration. But I don't know the centripetal acceleration, so I can't calculate it. Right? I'm asked for a numerical answer here. They didn't say express it in terms of these other variables. They say calculate the tangential speed. So I can't do it that way. Some students try to use kinematics. If you're using kinematics, then you're doing the kinematics, simple harmonic motion kinematics, which we don't do a lot of in this class, which you could do, but the easiest way would just be, remember it's tangential speed, not tangential velocity. Right? We just need to know distance over time. Don't care about direction. So I literally could just say that the speed is distance over time. Because if the time is the period, which we call capital T, right? That's the answer to AI. Period is 120 seconds. What distance did I cover in one period? One rotation. And so how can I write that in a way that I can calculate it? Circumference. 2 pi r. If you forget your circumference equation, by the way, that's on your formula sheet. Yeah, it's just 2 pi r over t, and it comes out to approximately, I think, if I remember correctly, 1.6 meters per second. So a lot of people overthought that one. Just distance over time. That's the easiest way. Again, you can use this graph, but you gotta know calculus to use this graph to come to that conclusion. Even that, yeah, this is the best way, by far the easiest way. Okay. Number B, on the dot below, which represents the book. Draw and label the forces, not components, so they remind you, don't put components here, you might lose a point. That act on the book at the lowest point of its circular path. Each force must be represented by a distinct arrow starting on and pointing away from the dot. For this particular free body diagram, you didn't even need to have the lengths of the arrows proportional to each other, or relative, the relative size that they should be, because pretty much the rest of the problem deals with really which one of those should be larger, if any of them. But at the lowest point, right here, when the book is right here, and remember it's moving this way at a constant speed. So someone brought up last period that there could be friction here. There's not going to be any friction at the very bottom. At the very bottom, the book and the table are simultaneously moving to the right at the same speed. VB starts getting smaller as it starts going up this way, which means there has to be a friction force pointing this way after it starts rising. But right at the bottom and right at the top, there's going to be no friction force, right? So I don't want to delve too much into that. But at the bottom, there's no friction force. Hopefully you can kind of reason that. So the only two forces that are acting are the normal force and the weight force.
How is not the force of the bench?
That's the normal force.
Okay.
Yeah. So if you put an arrow pointing up and said F bench or FB or whatever, then yeah, you're fine. You don't have to say it's a normal force. You just have to indicate that it is the force from the bench on the book. Now, some people do this. Don't do that, guys. There's 3 points for this. Some parts of this, some parts where you have to do a bunch of calculations were worth 2 points. This free body diagram was worth 3 points. 1 point for that guy, 1 point for that guy, 1 point, one additional point for not putting any extra arrows. Okay? So this person would have got 2 out of 3 because they put that V there. If they didn't put that V there, they would have got 3 out of 3. Force, they put velocity on force diagram. It's. I know I call them free body diagrams. They're free body force diagrams. Only forces go on them. Only forces. Some people did this. This might actually, if you label it this way, this might actually cause you to lose a point. Never label a force as centripetal. Okay? A centripetal force happens because another force is acting as the centripetal force. So you want to indicate what force is actually causing it. And then I also had some students do this. Right? Putting the centripetal force as an extra force. Okay? If you can't identify, well, what is this? What's causing this? You can't answer that question because there's literally nothing causing it. Right? So don't put it. If you're going to put a force on a free body diagram, if the diver's going to feel a torque and you're saying there's a torque, well, what force is causing it? Right? He's already left the diving board, so what force is causing the torque? Well, he's doing this. That's not force. That's not force. Well, there's forces involved with that, but those are internal to the system of the person, so they're not going to create a torque on the person. Okay? So I always ask you, when you're doing a free body diagram, these should be easy points. So ask yourself, if you're putting an arrow, what does that arrow represent? Make sure you can answer that question. If you can't, that very likely means that you shouldn't put it. So those are the forces. At the lowest point of the circular path, the book is moving only in the horizontal direction. In what direction, if any, is the net vertical force on the book? They trick you. They're tricking you with this one. They're tricking you. We know that the speed is purely to the left. So what direction is the net force if the object's moving purely to the left? A lot of students get this out of your brain. Get this out of your brain, and you'll definitely be guaranteed to get some extra points on tomorrow's exam. This person is moving to the left. If the net force was 0, it would just keep moving to the left in a straight line, right? If the normal force was the same size as the weight force, meaning that the net force doesn't point in any direction, then the book would keep moving to the left at the same speed as Mr. Jacob just said. So what's preventing that? The normal force has to be larger than the weight force, so that you have a net force that points toward the center of the circle that the object is moving in. Remember centripetal. Centra comes from some Latin root word that I don't know that means center, and pedal or pedal or whatever, that means seeking, kind of, from what I've been told. So center seeking force. That means the net force, if I had drawn my free body diagram correctly, I would have drawn my normal force larger than my weight force. Okay. So the answer to that one, in what direction, if any, is the net vertical force on the book? Up. Without deriving any equations, briefly explain your reasoning in terms of the book's motion. The book's moving in a circle. It's at the bottom of a circle. Therefore, if it's going to continue moving in the circle, the net force needs to point towards the center of the circle, which means the normal force must be larger in magnitude than the weight force. You could probably explain that in less words, but I'm not a good Englisher. All right. So I'm going kind of fast, but I want to make sure we get this done, and I have a couple minutes to talk to you all at the end. Derive an algebraic expression for the vertical force that the bench exerts on the book at the lowest point of the circular path. In terms of the books, guys, pay attention. This is on my little sticky note here. Things to definitely make sure I highlight when we go over this problem. Derive an algebraic expression for the vertical force, meaning the normal force, in terms of the book's mass, mb, tangential speed, vb, and radius r of the path. And physical constants as appropriate, which usually means g, little g. Do not substitute any numerical values for variables or constants. So they just want an equation. Okay. We're analyzing forces. We know the object has a centripetal acceleration, so we're going to invoke Newton's second law, where the net force equals the object's mass times acceleration. It is moving in a circle, so that acceleration is centripetal, so the net force must also be centripetal. Towards the center of the circle, always positive, whether it's at the top or the bottom. Call towards the center of the circle, define that coordinate system. Towards the center of the circle is positive. So I have a positive normal force. It just keeps you from having to deal with too many negatives. A positive normal force, negative weight force, that equals mass times, what are we looking for? Normal force. Mass times acceleration. And then I just add mg to both sides. So I get that the normal force is mass times centripetal acceleration plus mg. All right. There, I'm done. And I haven't maximized the number of points I got. I lost at least 1 point, maybe 2. Because it says derive an equation and express your answer in terms of the book's mass, which I got. Tangential speed, which is not there. Radius r, which is not there. And then I have centripetal acceleration, which is there, but can't be because it's not on my list. I'm seeing this a lot as I grade the FRQs, the review FRQs. A lot of students are answering these kind of questions with variables that aren't in the list of things that can be in your answer. You will not get full credit for that. Okay. What that usually tells you, like dealing with a projectile, you get your answer, but it doesn't have, you have things in there that can't be in there to get full credit. Well, I dealt with the y direction. So now I just get another equation by dealing with the x direction. And then I combine those equations and I'm good to go. Same thing happens here. Centripetal acceleration can't be there. So I need another equation for centripetal acceleration. Well, I know that. It's on the formula sheet. Speed squared over r. And look, so I realize I got something there that's not there. Right? You don't have to have everything that's in your list. Very often you do, but you don't have to. And so if you have something in here, though, that can't be in there, then you get another equation. And then I see that, and I'm like, all right, well, then I just substitute that in. I get mv squared over r plus mg. mvr, fundamental constant, m again, we're good. And there's your answer. Okay? And part D is kind of the same as a previous one. At the lowest point of the circular path is the force that the bench exerts on the book greater than, less than, or equal to the weight of the book. It's another way of asking the same question. It has to be greater than. It has to be greater than. And it says briefly explain how your answer in B double I and C support your selection. B double I we already answered. It's because it's moving in a circle, so the net force has to point towards the center of the circle. This equation, if you think about it, if you engage your brain when looking at this equation, it clearly shows that the normal force has to be bigger than mg. Normal force, if it was equal to mg, then this term wouldn't be here. But because this term is here and is not negative, this is a positive term, I have to take mg, then I have to add this quantity to it in order to get the magnitude of the normal force. So it must be bigger, right? Again, if it's not moving, then Fn equals mg. But as soon as it starts moving, when it's at the bottom, then Fn is going to be this plus mg. Right? So I've increased the right side of this equation, which tells me that the normal force had to increase. Go Beans? All right. Some last minute stuff. I'm going to send out a remind later today to watch that 8 general strategies video again. Again, I pointed this out early in the period. If you struggle with some of the initial questions, don't let that color your whole attitude. Know that you don't need to do stellar percentage-wise to get a good grade on this exam. If you get a 55, you probably got a 4. If you get a 70 or above, you got 5, and you knocked it out of the park. Okay. So if you get a few questions that are like, don't let it beat you down. Don't let it beat you down, because then what that does psychologically, it sets you up to just fail on questions that you otherwise would have done fine with. The 8 General Strategies video, I feel like the best tips are the following. You get your free response question section of the exam. It's 5 questions. Skim through every single one. Don't read thoroughly. Don't take a half hour of your hour and a half time to read every single one without actually doing anything. Take 5 minutes or so to skim through each free response question, and then identify which ones that you are more comfortable with, that you understand the material better. Identify which concepts, right, are going to be assessed. And then at least number them 1 to 3 or 1 to 5 if you can. Don't take too much time trying to do that, but definitely identify the ones that you're most comfortable with and make sure you get those done. The point is, what if you do and this is like the prime example. You start question 1 and you scratch your head a little bit and you're not really sure what to do, and so you try a few things and then you figure out that didn't work, and so you try something else and you're just lost and you don't know what you're doing, and you end up spending 20, 30 minutes on free response question number 1, and then you just move on. And when that question gets graded, you get like 1 out of 13 points or 5 out of 13 points. But because you took so much time on that first question, you don't even get to question 5. But question 5, you would have blown away. You would have known it. You would have known how to do question 5, every single part, and you would have gotten your 13 out of 13 or 20 out of 20 or whatever points you get. You would have got them all. But you don't get those points because you didn't have time, because you wasted too much time on the problem that you really shouldn't have wasted any time on. So skim each question, pick the ones that you're the most confident with, and do those ones first. Okay, that I feel like is the free response is going to make or break you. The multiple choice at this point, without some last minute tweaking like ideas of momentum, angular momentum, and centripetal motion that I talked about today, your multiple choice, there's not much you can do at this point. You can do some last minute review, but the free response is the one that's more strategy based. Yes, you obviously have to know physics, but you can utilize strategies to maximize the points that you can get on them. So do that. And also, again, that free body diagram, 3 points. This one right here, I think it was 2 or 3 points. So these were equally weighted. This might have even been less. This might have been just 2 points. It was 3? This one? Okay. So pretty much the same. This, if you know what you're doing, takes a few seconds. This takes at least a few minutes. There are some problems where there's just real dense algebra. When you got to analyze an Atwood machine with a massive pulley, so you got to do Newton's laws of motion for tangential, or Newton's laws for translational motion, and then you have to do Newton's laws for rotation, and you end up generating 2 or 3 equations that you have to tie together, right? That takes time. That takes a lot of time. And so if you find yourself spending 20 minutes doing algebra for a single part of a single problem, you are not making good use of your time, because you're probably only fighting to get a couple points. And then again, you might sacrifice some points later on something that you should have gotten points on many times, many more points than by wasting the time just doing algebra. So as Mr. P says, leave those till the end. Finish all the problems that you're super comfortable with, and then go back and work on the math, right? The math that takes a while, the tedious algebra, and then try to get some partial credit on the questions that you're not too keen on, but you don't want to leave blank anyway. You lose no points for not attempting. You lose no points for wrong answers on the MCQ portion of the test. So that means if you got 2 minutes left, if you got like 30 seconds left and you got 5 more questions, it's abacadabra, or all C's, or whatever your method of multiple choice guessing is. And then remember that the last few questions are going to have you answer two answers to each question. So just, it'll say it, select 2 answers. I'll put parentheses, select 2 answers. So just make sure you're reading the questions thoroughly so you know that that's going to be there. Other than that, units on your answers. Like the first one for the Ferris wheel one is 120 seconds. If you put t equals 120, I'm not saying they will take off points for it, but I'm definitely not saying they won't. They might. Don't know. Depends on what the scoring guidelines happen to be for the particular problems that you'll be working on. Show all your work. Students are losing points. They lost points on the FRQ portion of the mock, and as I'm going through the FRQs for the review, students are losing points. And you know they did it right. You know they're real smart, so they can do most of it in their head, and so they just write down the answer, but they show no work. But I'm scoring it. I'm grading based on what's in the scoring guidelines. And so in the scoring guidelines, if it says 1 point for the answer, you get that 1 point. But then there's 4 more points for all the parts that lead up to the answer. You don't get it. You don't get those points. So make sure you show all your work. Okay. Again, I'm going to send out a remind to watch the 8 strategies video again. Please watch that video and don't just watch it. Internalize it. Implement the strategies. And you will. There's ways of increasing your score on the exam literally without having to learn any more physics. That's what that video is all about. So please do that. One other thing. When a question, your experimental design question, where you have to design an experiment, pick what quantities you're going to measure, stuff like that, what you're going to graph, things like that. Always in your experimental description, mention that you will repeat the experiment several times. Repeat each trial several times to average the result. Because if you just run a trial one time, there's a lot of experimental uncertainty. If you repeat the trial several times and you get similar results several times, then you can be sure that you're pretty certain. Sorry. And generally, there's a point for that. Generally, and it will say 1 point is awarded for the student addressing experimental uncertainty. The easiest way to address experimental uncertainty is to say, repeat the trial several times and average the result.
That's on the FRQ?
That's on the experimental design FRQ. Yeah.
What are those? Is that like?
This is one where it asks you to design an experiment to.
Okay.
Like, hey, what quantities would you need?
Yeah.
And explain step by step how you complete it.
So in your explanation, just avoid losing that 1 extra point by saying repeat each trial several times.
Okay.
And then you're good.
What kind of experiment is it, like kinematics?
Who knows?
You use the duct tape provided to attach string to the wall.
You don't have to be that detailed. You don't have to say you would say attach string to the wall or ceiling or whatever. All right. I think that's all I got. Any questions? Last minute questions? Because I'm probably not gonna see y'all before you take the test. So,
I
'Cause-
have a question.
yep.
The physics test starts at 11:30, right?
Yes, sir.
So why would we?
At 11:30?
Yes, sir.
Yeah.
Oh my.
So why wouldn't we see you?
Bruh.
Because you have an EOC tomorrow.
What are you gonna EOC tomorrow?
Oh yeah.
And your EOC whoever's running the EOC should let you out with enough time to eat lunch. So they should let you out before your lunchtime. Why is that so distressing for you?
Like 2 hours?
That's what I'm saying. Finish your EOC real fast because I know you guys can, and then take a nap. Get nice and rested.
I thought it was gonna be at like 1.
No, it's 11:30. Yes, ma'am.
Do you think if all the physics kids finished their EOC, they would let us like get our stuff and look over stuff?
I don't know.
Actually, all of us in one class, so we should be done relatively fast.
You're gonna have to ask whoever's running it. I have.
If everybody's finished within like what, the first hour?
You know, Brock's gonna sit there though and fall asleep at the beginning, and then not be done until like 3 hours in.
Rob
Though.
was the first one to finish yesterday.
Oh, never mind.
Boy, I was the first one.
All right, bye everyone at home.